Okay, so we're gonna look at the cases where how the repeated game is analyzed, and what's the main difference from the one-shot game and the repeated game. So I've changed my mind a little bit, where I told in the previous lecture I'm gonna focus on this sequence, but let me just talk about this case 1 and then case 3, because it really captures the real essence of the repeated game for the cases where well, the case 2, well, we can study this case in the future, right? So let me talk about this case, and then we will see how the result would differ when we have a finite game or an infinite game, and also compare the result between those two, right? So first, let's look at the finite repeated game. So finite repeated game is that the round stage, it's a number of stages, is finite. It's predetermined, right? All right. So again, we're gonna look at the prisoner's dilemma. I slightly changed the payoff, but it essentially is equal to, I mean, the real feature of the prisoner's dilemma is same as this and same as this and so on. Okay. Oh, just the numbers have been changed, so it all captures the real essence of the prisoner's dilemma. So whenever we have cooperate, then we have this payoff and defect, and we have this payoff and so on. Obviously, the Nash equilibrium is this. Okay, whereas both players probably prefer this cooperation CC, but what unfortunately the Nash equilibrium is this. That's what we know, right? Okay, so the question is, what happens if the game was played finite times? Then, well, since this is again the dynamic game or the sequential game, well, it's not it's not exactly a sequential. It's a dynamic game, so we need to look at the subgame perfect Nash equilibrium for a more perfect equilibrium concept. So we're wondering about what would be the equilibrium, where we're mainly interested in the sub-perfect Nash equilibrium. And please recall that the sub-perfect Nash equilibrium can be computed by the backward induction. So backward induction can be regarded as an algorithm to find sub-perfect Nash equilibrium. So in order to, okay, so I mean, this game will be repeated, right? It's like something like this: 1 time, 2 time, 3 time. And we have some t time, or t stage if you like. Then in order to run the backward induction, then obviously we need to go toward this direction. So we first look at the game where only we see the one stage game in the last period, or last stage if you like, right? And then what would happen? Well, obviously, well, in the last period, when we just look at this game, this last game, and this is just a one-shot game, one-stage game. So obviously the defect is a dominant strategy, regardless of the history of the game, right? Because we are looking at the last game. Okay. So the sub game starting at T, which essentially where we the remaining game is just a one-shot game, has a dominant strategy equilibrium like D, D, and that's what we know, right? This is a Nash equilibrium for the one-shot game. So when we focus on the last period game, then the D, D is a equilibrium. Now, assuming that we know that or D, D is determined as a Nash equilibrium, then now let's look at this game, like this two-stage game. Again, I'm running the backward induction, all right? And then we know that the DD will be played. And then obviously here in this case, we know that no matter what happens, the player will be chosen. I mean, that which will be chosen by the player will be the D, D, right? Otherwise, the main reason is that, well, if we choose other strategies like C, D, D, And if we choose other strategy, then obviously that's not a Nash equilibrium. Okay? So then given this, then the subgame starting at the t-1 also has a dominant strategy. So in this manner, then the last game d comma d is the Nash equilibrium for the subgame of the last round. And then if we go upward like two-stage game, and then d comma d is still Nash equilibrium. In this way, we can say that for the finite stage game, then the like playing like d comma d comma d comma d, or let's say player 1 like d d, and player 2 d. This strategy is a sub game perfect Nash equilibrium. I'm running the backward induction. Okay. In order to check more seriously, so let's look at d comma d and like t rounds, t stages. Look at that. Let's look at this. Okay. So suppose that we are looking at the subgame of this. Okay. Again, in order to satisfy the definition of the subgame perfect Nash equilibrium, what's the definition of the subgame perfect Nash equilibrium? For every subgame, then the strategy that is restricted to that subgame should be the Nash equilibrium. I claim that d play 1 and play 2 d. This is a subgame perfect Nash equilibrium. So in order to check that, let's first look at some arbitrary subgame. By cutting the round from this point on to the last round. All right, and then I claim that from the perspective of the S1, then the choosing D is a better strategy in some sense. Okay. And then we can think about this case for the player 2 as well. But I'm looking at the case where instead, rather than choosing DD, let's see what happens when the player 1 choose a different strategy like C here, and then D always. Okay. All right. So when we compare these two cases. Where if player 1 chooses C here, then obviously the payoff of the player 1 comparing the payoff when player 1 chooses C or D, we'll look at that. Well, this is player 1 and this is player 2, and whatever P2 chooses, like C or D, I have a higher payoff when I choose D, right? See, compare 2 and 3, compare 0 and 1, right? So in this case, by choosing D, I have a higher payoff in this T stage. I have a higher payoff, right? That's actually irrespective of how the player 2 chooses a strategy. Okay? And also, D and D comma D, and by choosing D here, and irrespective of this strategy, like D comma D is 1 comma 1, right? I'm choosing D here, I'm choosing D here, but suppose that this is D or C. It can be chosen by this player to like D or C. The DD is just the same as this one, but the DC is what? DC is I'm choosing player 2 choose C. And then I'm comparing the payoff when I play D and D, where the player 2 chooses D, and which should be 1. Here in this case, the payoff is 1. I'm talking about player 1's payoff. Alright? So this should be payoff is 1. And when the player 2 chooses C, then my payoff is 3. So whatever the strategy is chosen by the player 2, by choosing D is the best response. I mean it's good. I mean it's better than this one. So we have this relationship. So what does this tell? What does this example tell you? Well, when we look at an arbitrary sub game, the player one's perspective, choosing D is the better response than the like choosing C here, and the rest of them are D. And then we can see like okay, if we include like C here or C here in arbitrary stages, it's always choosing D is better. So this is not a good strategy. I'm checking P1's strategy in any sub game starting from the stage T. Choosing D is better than any choice of other strategy for a fixed S2's strategy. Alright, and this thing can happen similarly for the player 2 because the game is symmetric. Alright, I'm sort of elaborating on this argument for those who does not accept this statement clearly. Alright, and for this region, again, as I mentioned before, playing D at player 1 and player 2 D is a sub-perfect Nash equilibrium. Now the question is that, well, we need to check whether this sub-game perfect Nash equilibrium is unique or not. Like is there any other sub-game perfect Nash equilibrium? Well, when you do the math, I'm not going to do that, but when you analyze this game more, then we can see that it's actually the unique. So we can have some theorem that consider a repeated game GT where discounted vector is delta. So for any delta for the finite round, and suppose that the stage game G has a unique pure strategy equilibrium A star, like prisoner's dilemma. Then the GT, which is a repeated game, has a unique sub-game perfect Nash equilibrium, which corresponds to the strategy of the playing the Nash equilibrium strategy for the one stage game, always for the entire round or entire stage, regardless of the history, is the sub-game perfect Nash equilibrium. I mean, we can easily extend this kind of the argument or the discussion to the theorem. I'm not going to prove well, even if there's a very short line proof. I'm trying to convey the basic idea. Okay, so in this case, I mean, there's no cooperation appear even if we repeat the game. The reason I'm telling you about this thing is that, well, in a repeated game, probably there are some cases where some kind of the threat of the punishment or the threat of the retaliation may induce some cooperation, but when the round or the number of the stages are finite, then actually we cannot see those cooperations. The reason is that since I know the end of the game, which may not affect the game's behavior compared to the just one stage game. Okay, so essentially the behavior of a repeated game for the finite stage, whenever we have a unique pure Nash equilibrium, then it's almost like equal to the one-shot game or like a 2-round game or a 3-round game whenever this is a finite. Of course, when this condition is broken, like stage game may have a multiple Nash equilibrium, right? We saw the example of other cases like coordination game. We see the 2 Nash equilibriums in one stage game. In that case, well, different thing happen. But I'm sort of I'm trying to restrict our attention to the case where stage game has a unique Nash equilibrium, and then what happens to the repeated game when we have a finite round. And then we have this theorem, and which follows our intuition. Since the stages where the number of rounds are finite, I can sort of predict when this game will end. So I will like behave just as if I play the one-shot game for just one round. Okay. All right. This case is pretty easy, but now interesting thing can happen when we have an infinite repeated game. Okay. Now infinite repeated game. Now important factor that may affect is the discount factor. So remember what the discount factor is. So discount factor means that, well, actually I will continue this game with the probability, some probability, and I will end this game with some probability. There's only exists a probability of ending the game, which means that I actually don't know when this game will end. I have just roughly have an idea about, okay, 1 over minus delta is the like average rounds of the game, right? Average number of rounds. Because yeah, this is a geometric random variable, right? So I have a delta probability. I'm going to end the game with the 1 minus delta probability. So the average number of rounds that I will experience is 1 over 1 minus delta. But that's just an average number of rounds. I don't know. Well, it can, like, depending on the coin that I'm gonna toss, with some probability my game can have around like 1,000 or maybe 10,000 or millions of the rounds. It's possible. There's a probability, right? So now the infinite repeated game. Then since I don't know when the game will end, there are some interesting philosophy or the morale can be inserted into this game so that we can see something interesting. Okay, so we're gonna look at this case. All right. So let me just give you some intro about the the repeated game. So an infinitely repeated game usually has more subgame perfect Nash equilibrium, which is pretty much different from the finite repeated game, where the finite repeated game is just what subgame perfect Nash equilibrium is like play D D D D D, play D D D D D. But we have other much more other like interesting strategy that is actually the subgame perfect Nash equilibrium. Okay, so it may have a multiple subgame perfect Nash equilibriums even if the stage game has a unique Nash equilibrium. All right, we will look at that. But playing the Nash equilibriums in each stage game, like D D D D D, obviously regardless of the history, is still subgame perfect Nash equilibrium. But I'm saying that in addition to this strategy, there could be more. That's the key point. Okay, so the playing D D D D D D D D D D is also sub perfect Nash equilibrium, but we have more than that. Okay, all right. So the playing D D D D D, like defect, is a subgame perfect Nash equilibrium. So our interest is the strategy inducing the cooperation is a subgame perfect one not, because as I mentioned before, as I give you some motivation that about this repeated game, well, it's possible that I can threat my opponents by the based on the punishment philosophy, so that my opponent and I may cooperate and choosing like C C C C C. Okay, so let's look at what happens. All right, so let's first look at a very interesting strategy, T for 10. All right, so this strategy is described as follows. So by the way, in terms of the strategy, there could be on very simple strategies. Like playing D D D D D, or playing C C C C C C. So unconditionally, I'm going to choose the D D D D D C C C C C are all strategies. I mean, these are the strategies. Or maybe you can choose a strategy that I'm going to alternate between C and D. C D C D C D. This is also another strategy. Or D C C D C C D, C, C, S4. So any deterministic choice of the sequence between the D and C, whether D can like D, 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 C, C, D, 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 C, C, or D, C, D, C, D, C, D, C, D, C, 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 D, D, are all strategies. But I'm going to look at an interesting strategy that is not very trivial in some sense, which is called the T410. Okay, so T410 strategy is described as follows. First, I'm going to start with the C. Okay, so I'm going to start C, and then do whatever the other player or my opponent did in the previous period or stage or round. Alright? Okay? Which means that, okay, this is player 1 and this is player 2. And suppose that, so player 1, player 2, suppose that the player 1 is using T for tat. And suppose that player 2 is choosing like D, 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 D strategy. Okay? Like player 1, and he's choosing T for tat. Okay? So what would be the sequence of the player 1 if player 1 chooses T for tat? Well, they first start with C and do whatever my opponent did in the previous round. So in the previous round, the player 2 played D, so I'm going to choose D, and my opponent also choose D, and D, D, D. Okay, so depending on the what strategy is chosen by the P2, the outcome of T4 strategy could be different. Do you remember that I differentiate between the strategy and outcome for the extensive form game? Okay, probably you remember, right? For this instance, for the P2's strategy D, 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 T4 strategy's outcome is C, D, 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 D. And suppose that P2's strategy is not D, 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 but D, C, D, C, D, C, and so on. And then obviously the T4 strategy's result would be different. How? They start with the play C, and they sort of copy the strategy that is chosen by my opponent in the previous round. So I'm going to copy like D, and I'm going to copy C, I'm going to copy D, I'm going to copy C, and so on, right? And that's the outcome of a T4 strategy. For the P2 strategy, this. Okay, I'm highlighting the notion of the strategy for the extensive form game as well as a repeated game. And when we draw the T4 strategy using a finite state machine, then probably this is the figure, right? So this is this arrows is arrow means that its opponent moves, right? So suppose that my current state is C, and the strategy that is chosen by my opponent in the previous round is C, then I'm going to copy that. If that is D, then I'm going to copy that. So my state changes. If this my previous strategy of my opponent is D, then my state will be again D. And if that's C, then C. It's basically the copy the previous round of my opponent. So I'm sure that you have a complete understanding about the T4 strategy. Okay. All right. Good. So that's the T4 strategy. Now let me ask the question. So we're gonna ask the question one by one, so that we can have a clear understanding about what happens in the infinite infinite repeated game. All right. So what does the T4 do when playing against these strategies? Okay, I'm just going to describe how the T4 behaves. So when my opponent's strategy is D D D D D, then I'm start with the D, and then I'm going to copy my opponent's strategy. So that should be the C D D D D D, right? My opponent's strategy is always cooperate, like C C C C C. Then I'm going to choose C, and then I'm going to copy my opponent's strategy. So always cooperate, C C C C C. That's what we have, right? Now my opponent's strategy is the T4-10. Okay, let me first look at this case. So my opponent's strategy is DC, 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 DC. Then my strategy will start with C, and then I'm going to copy this guy, DC, DC. So C, D, C, D, C, D. That should be this. Okay. Now my opponent's strategy is T4-10. And then my strategy also T4-10. Then what should be the outcomes? And the outcome is that my opponent is, let's say this is a player 2, and this is player 1. And the player, this is my opponent. Okay, let's see, this is opponent. And this is me. And the opponent is T4-10. So they will start, he will start with the C, and me, I'm going to start C, because I'm using T4-10, and my opponent is also using T4-10. Okay, and then I'm going to copy the previous round, and this guy is also copy, right? So the strategy should be right. C is copy, C copy, copy, copy. So C, 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 C is the outcome. So that's why for the T4-10, if my strategy is T4-10 also, then I always cooperate. That's exactly what I have here. Make sense? So I'm just giving you the explanation about how T4-10's outcome will be depending on the strategy of my opponent. Good. Now you probably have understanding about T4-10. Now let me ask another question. Out of my opponent's strategy, like D D D D D or C C C C C, suppose that I'm playing T4-10. This is me. Then this is opponent's strategy. Is like always D strategy, or always C strategy. And then I'm going to look at, or I'm going to determine which is better response to the T4-10 for me. Okay, let's look at this. This is opponent, and this is me. So I have assumed that I have these two strategies, always D or always C. So I'm going to choose either of this strategy, which is the better response to the T4-T. Better response means that what's the strategy that gives me a higher payoff. Okay? So so I have to compare the payoff when I play this guy or this guy, assuming that my opponent plays T4-10. Okay? So this is me. And what I'm doing is that first let's look at this case. And I'm playing D, 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 D. And my opponent plays T4-10. So his strategy, he start with C, and he just copy my strategy. That's what the T4-10 is. Is that true? And what is the payoff of my D, 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 D? That should be DC. So suppose that this is me, and this is my opponent, and the opponent chooses C, and I'm choosing D. So my payoff will be 3 plus, and I have a discounted factor, right? Now D, 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 D. So D, 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 D is always 1. So in the second round I have a delta plus delta square plus delta cube and so on, and that should be 3 plus delta 1 minus delta and delta. That's my payoff. Okay, good. Now let's compute my average discounted payoff. Here, I'm choosing C, and my opponent is T for Ted. So he start with C, and he just copy my previous round, C, and so on. This is outcome. Now the payoff of this guy is at CC. It's like 2. It's like 2 plus delta plus, or 2 plus 2 plus 2 delta plus 2 delta square plus 2 delta cube and so on. And that is 2 1 minus delta over 1. Is that right? Okay. Alright. Now the question is that, well, probably depending on the value of the delta, this may be larger or this may be larger. Okay, so let's find the point where this value becomes equal to this guy. So 3 plus 1 minus delta is equal to 1 minus delta 2. And if we multiply 1 minus delta in both terms, 3 minus 3 delta plus delta is equal to 2. And that should be 2 delta is equal to 1. Oh, delta is 1 over 2. Right? Now if you compare these two payoffs, and if in the intersection point of the delta is 1 over 2, it becomes higher than 1 over 2, then this becomes larger. Oh no, sorry, the other way around. This becomes larger. But when delta is smaller than the 1 over 2, this becomes larger, which means that always choosing D is good for low delta, but always choosing C is good for higher delta. Okay, now that's quite intuitive. Why is that? Because look at that. Look at the outcome of these two cases. When you compare these two cases, this case is always cooperate. They cooperate, always cooperate, right? So they are actually this is a cooperation game. All right. But this is what? This is a one deviation. Deviation means that when the opponent chooses D, but opponent chooses C, but I'm choosing D. And when I'm choosing D, when my opponent C, then its short-term gain is high. This is a short-term gain. But after that, it's what? It's a payoff from defect. I mean, it's a payoff from the non-cooperation. Right? This is a what? 2, 2, 2, 2, 2. This is 1, 1, 1, 1, 1. But this is 3. So in order to get a higher value of the payoff in this case, then what? This future payoff should be larger. Which means that the game should last long and long and long. In order to make the game last for a long time, we should have a higher probability of the delta, because the 1 minus delta is the probability that I will end the game, and the delta is the probability that I'm going to continue the game. And that's why this result is pretty natural. So when the users are more patient, then the players may or each player or one player or players have a higher incentive to cooperate, if you look at that. But again, well, I'm not still talking about what the equilibrium or sub-perfect Nash equilibrium or Nash equilibrium, whatever. I just compare the strategy of the DDDDD and CCCCC as a response to my opponent's strategy, which is T for 10, in order to see the trend of what would be the better strategy for the T for 10 strategy. Right? Good. All right, now let's look at that. I'm going to look at the best response to some strategies, where the some strategy is this. So given this strategy, I'm going to look at what is the best response of me. I'm particularly, this is delta, sorry. I'm particularly looking at the case where the delta is 1 over 2. Delta is 1 over 2 is this regime, where I have a higher incentive to cooperate. Okay, and the game will last relatively long. Okay, all right. Now, so let's look at that. So in order to make the explanation easy, let me show you the another also the finite state machine, and that finite station is actually the same as the previous one. That I'm just a little bit changing the how to use this this state machine. So different from the earlier case, I have changed it to in the I mean, the earlier case, the opponent move was the arrow, but here let's assume that the opponent state, this is opponent state. So state is the opponent choice, and these arrows are my strategy. Edge is my choice. This edge is my choice, and edge level is my payoff. I mean, I can switch my opponent position and my position. That's what I'm saying. All right. Okay. Now, given the strategy means that okay, if my opponent, suppose that this is my opponent, if my opponent chooses always C, then what is the best response of my my strategy? Like always C or always D or always T for tat. If my opponent's strategy always D, then what is my best response? And if opponent's strategy is T for tat, then what is my best response? Okay? Suppose that my opponent's strategy is C. This is my opponent's strategy. And this is my strategy, could be always C or always D or always T for tat. Now always C is the C. Or always D is a D. So let's look at the payoff. What happens? So if my opponent is here in the C, then by choosing C, I'm going to get 2. But by choosing D, I'm going to get 3. And then if my opponent's strategy is C, then obviously choosing D will be the best response. Right? Otherwise, if I choose the T for tat, then what happens? I'm C and C. This is my T for tat for the opponent strategy of the C. So that's why this is the best response. Okay. Now let's assume that my opponent strategy is D. Then my choice can be always C or always D or T for tat. T for tat is start with C, and then I'm going to copy my my opponent's strategy. What gives me a higher payoff? Well, DC is that my opponent's strategy is D. Then if I choose C, then like 0, right? 0. My opponent is D, then if I choose D, then I'm 1. Of course, we need to discount the payoff. And that's 1, and T for tat. If I play the T for tat, I get this, and the DC is what? DC is 0, and D 1. So obviously this is the best response. That's why this is the best response, right? Okay. Now what happens in this similarly? What happens? My opponent's strategy is what? is T for 10. So they start with the C. So my opponent start with C, and then I can what? I can choose always C, always D, or T for 10, right? If I'm choosing always C, 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 then my opponent will copy my strategy. That's one case. And another case is my opponent is playing T for 10, so start with C, and I'm choosing D, 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 and he will copy my strategy. That's another case of this guy. And my opponent plays T for 10, and also I'm also playing T for 10. So C and C, T for 10. Oh, I see. So this guy's outcome and this outcome is the same, which is a larger payoff of the middle guys. And that's why my best response is this guy as well as this guy. And probably the most interesting case will be this, right? All right. In this table, I mean there could be other strategies, but let's restrict only this strategy for both players. What is the Nash equilibrium in this case? Yeah, you should have the same guy, right? So this is a Nash equilibrium, like D D D D D D D D D D, or like okay, say always D, always D is a Nash equilibrium, or T for 10, T for 10 is a Nash equilibrium. Because it's the best response to each other. Okay? So those are the Nash equilibriums. As I mentioned before, these are the Nash equilibriums. Is there any cooperation in the Nash equilibrium? Yes. Do you remember that in the finite repeated game, just always D and always D and always D was the Nash equilibrium as well as the subperfect Nash equilibrium. But here in the infinite repeated game, always D and always D are Nash equilibrium. I didn't talk about the sub-game perfect Nash equilibrium yet, because in order to discuss that we need to consider all the sub-games. But I'm not saying we are not looking at all the sub games. We're just looking at the entire game, right? It's like a whole sub game tree. All right. So still, it's too early to talk about the sub game in Nash equilibrium, but sub game perfect Nash equilibrium. But in the infinite case, at least we are talking about the just pure Nash equilibrium, where either we can have this as well as T for 10, T for 10. And what is this outcome of this strategy? That's C, 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 C. That's interesting. Why is that? Because in the finite repeated game, there's no cooperation because everybody is due the defect. But here in the infinite repeated game, we have a Nash equilibrium which has the total cooperation as an outcome, which means that the T for test strategy and T for test strategy. Why is that? What happens in an infinite repeated game? Why is that? Well, because, see, look at this one. What is a better response to the T for 10? I'm always playing C or probably T for 10 because the outcome will be same, right? Whether I play just always deterministically play like always C or T for 10, anyway, either of this guy and this guy is the better response. I'm repeating that. My opponent plays d4-10, and I'm also playing the t4-10, whose outcome is always cooperate. Why does that happen compared to the final repeated game? Because if I deviate from this, from t4-10 to t4-10 to other strategy, then I'm a little bit worried about the punishment or the retaliation, like 복수, right? Why is that? Because the t4-10, if I deviate from, like, for example, like c to d, then t4-10 strategy has a mechanism that he copy the strategy of my opponent, which means that he changes his strategy d, and then I copy D, then my payoff will be lower than the cooperation. So I'm a little bit scared about my changes, and that's why I'm going to sustain my strategy as cooperation. And that's what is behind the t4-10 strategy. What? As long as what? As long as I have a higher value about the future. If I have a low value about the future, then there's no reason why I choose to always cooperate, or t4-10, as we computed here. When we have a low delta, then obviously choosing D is better. That's why I'm assuming that the delta is larger than 1/2. Then in that case, t4-10 and t4-10 strategy, playing those strategy by both players, can become a Nash equilibrium. Does that make sense? So that's why t4-10 is still Nash equilibrium for small delta? No, obviously no. Right? And in that case, I'm more inclined to defect. Right? Okay? Again, remember, I'm still before talking about the subgame perfect Nash equilibrium. I'm just talking about the Nash equilibrium because I'm just comparing the entire strategy. I didn't look at like subgame like from this point and so on. I didn't do that. Alright? Okay. Alright, let's look at other strategy, which is called the Grimm trigger. Let me see. Yes. Which is the Grimm trigger. So the Grimm trigger is a more draconian policy than T4T. Draconian means that it's more brutal. So what is the strategy? Well, they start with the C. That's same as for the T4 strategy. Then place C if my opponent has played C actually. Yeah. C. But play D otherwise. Which means that if my opponent changes his mind from C to D, then I'm going to play D forever. Which essentially includes these things. Okay, so whenever we have a mutual benefit, then I'm going to cooperate. But whenever my opponent cross the line, which means that he changes the strategy from cooperation to the defect, then I'm going to deal out vengeance, 복수, forever. That's what I mean by more draconian policy than the T410. So when we draw this thing using a state diagram, then whenever I'm here at C, and if my opponent plays C, then I'm going to C. But my opponent defects and changes policy from the C to D, then I'm going to choose D forever. So what is the philosophy of the Grimm trigger policy? In some sense, well, I know that cooperation is good, but if you make a choice that is bad to me, then I'm going to revenge forever. Here, even if it hurts me, I'm not interested in my payoff. I'm going to kill you forever. Right? If you cross the line. So, well, this thing, I can smell there's some smell of incredible threat. Right? I mean, smell. Right? Because, well, I'm going to revenge you, but obviously since I'm rational, I need to think about my payoff also. Do you remember that the incredible threat in the extensive form game? I'm going to retaliate you irrespective of what's happening to my payoff. Well, that's not rational. The rational player will do something like, okay, I'm going to revenge you, but I want to still consider my payoff. That's how the rational player behaves, right? Okay. So that's Grim trigger strategy. Let me ask a simple question. So under what conditions of the delta the Grim trigger is in Nash equilibrium? So we looked at the case where the T4 strategy is becomes a Nash equilibrium when the delta is larger than 1/2, right? Yeah, larger than 1/2, because I have a higher incentive to cooperate when I have a higher value for the future. Now what happens to the Grim trigger strategy? When under which the Grim trigger is Nash equilibrium? The answer is, yeah, you can do complex math, but we can easily conjecture still that if the delta is greater than 1/2, then obviously GT is a Nash equilibrium, because GT then they start with the C and then they always cooperate when they start with the C. That is the outcome when the GT is played. Right? So in that case, obviously they will compare the payoff of playing always like plays always D and always C. Then Grim trigger is only different from the T4 TET when other guys are defect, right? But the payoff of always playing D and always play C would be the same. Okay, that's why we can have the result like if the delta is larger than or greater equal to the 1/2, then we can see the GTG is a Nash equilibrium. So it's a pretty